I'm going to take you through the concepts of entropy and free energy in this video. So let's start with the second law of thermodynamics. The second law of thermodynamics basically says that the universe is constantly increasing the dispersal of matter and energy. Uh, Basically, dispersal is another word for disorder. We're constantly increasing the disorder here of matter and energy. So essentially, disorder is preferred to organization. Right? So basic gist here is if you had a block of ice, right, and you just leave it set at room temperature, you know that it's going to melt and turn into a puddle of water. And that is preferred because this is organized, the ice is organized, and the puddle of water here is more disorganized. All right, so nature prefers this disorganized state, or we're going to be increasing the amount of disorder here in the universe in terms of matter and energy. We call this disorder or this measure of randomness entropy, and we denote it with the letter S. So anytime we see S here, we need to think entropy, disorder. Greater the disorder, greater the entropy. The more disorganized something is, the more the entropy value will be. Zero entropy, if you had zero entropy, that would be a solid crystal at 0 Kelvin. Essentially, there would be absolutely no disorder at all. If it's a perfectly organized solid at 0 Kelvin, you would have no disorder and it would be perfect. There would be zero entropy. Well, we've never actually reached 0 Kelvin, so all of our substances here will have a positive value for entropy. When we're doing these problems, none of the substances will have zero for entropy, kind of like we saw with enthalpy problems. Our pure elements and diatomics were zero. That's not going to be the case here for entropy because we've never reached 0 Kelvin, so we won't ever have a zero value for a substance. It's always going to be a positive value for the entropy or the amount of disorder here of a substance. Important to understand that you can have a process take place and the overall entropy be negative for the process. But for the individual substances, they will always have positive values, but sometimes a process can take place and the overall entropy of that process can be negative. We know here, we kind of already mentioned it, but disorder is preferred or favored in the universe here. Nature goes toward chaos, essentially. Just like we said, nature prefers this negative energy, this negative delta H. We also prefer this positive entropy here. All right. So important to understand here that kind of like enthalpy and entropy are kind of going to be opposites of each other, as you'll see as we kind of go through and do some of these things here. So entropy is the amount of disorder. More disorder, all right, more entropy, and we do prefer this positive entropy. Disorder is favored in nature. This idea of entropy and disorder is usually very easy to understand, and you can look at a number of situations here that kind of prove this idea. So obviously, if you were just one person here, you could be pretty well organized here, right? That'd be a low entropy, low disorder. Versus if you have a family with tons of kids, all right, lots of messes, that would obviously be more disorder, all right, this higher level of entropy. Another idea here to show entropy is imagine if you tossed bricks off of the back of a truck. What kind of pile of bricks would you end up with? Do you think if you threw all these bricks off the back of the truck, you'd end up with a perfectly organized, beautiful pile of bricks? No, probably not. You're going to end up with kind of this all messed up pile of bricks kind of all over the place, and that's more likely, and that's entropy here. This disorder is going to be more probable. Same idea here if you took, dye and added it to a solution. Over time, that dye is going to diffuse and spread out in the solution on its own because that makes it more disorganized, essentially. It's spreading out All right, it's becoming more disordered, which is preferred in nature. Liquids are going to have a higher entropy value than solids, so liquids are more disorganized than solids. Think about solids, they're perfectly organized, perfectly arranged, and then when you get to a liquid, there's definitely less organization there. So if we look at, a perfect snowflake, very nicely organized, very nicely arranged, low entropy, but then when you melt it, the entropy is going to increase. There's going to be more disorder there. Then obviously, if you go to a gas, you're going to have even more disorder. Gas molecules are further apart, moving around. All right, so gases are going to have a higher entropy than liquids. Obviously, here, if you have a solution, you're going to have more entropy than if you had just a solid. If you take a solid, put it in a solution here, dissolve it up, you're going to have much greater entropy, much more disorganization. Very important concept to understand. Obviously, if you had 2 moles of a gas compared to 1 mole of a gas, you now have more particles that can mix up, interact. You're going to have more entropy or more disorder. So definitely make sure you understand this in terms of solids, liquids, and gases for entropy, solutions having more entropy, and obviously more of a gas would be more entropy or more disorder. If you look at this picture, a solid is perfectly organized, perfectly arranged. You're going to have way less entropy, way less disorder. A liquid, a little bit more entropy there. There's a little bit less organization. But then when you put them together and you form your solution, you could see that would be the most disorder here, the most entropy compared to the solid and the liquid, because you have more disorganization taking place. So when you form that solution, you're definitely going to have more entropy or more disorder here. If we look at this picture here, we can see that as we increase the temperature, our entropy, our S, is going to increase as well. We're going to get more disorder here. So solids would have the lowest level of entropy, but then as you go and increase the temperature up to a gas, you can see that gases would have the most entropy here. And you can see that as you continue to increase that temperature, you're getting more and more of this entropy increase, more and more disorder as you increase the temperature. Again, just really driving home this idea of entropy and disorder, we know that anytime you have a solution forming, you're going to have more entropy. You can even see that here. You're very ordered, very organized solid. When you put it in a solution here, if it dissociates, all right, interacts with the water molecules, that's going to be much more disorder or an increase in entropy when you have a solution. In order to calculate the standard entropy change for a reaction, we're going to have to use this equation. And you should be pretty familiar with it because it's very similar to the delta H equation we were using. It's going to be products minus reactants again, but it's going to be a sum of all of your products here, and then the sum of all your reactants subtracted together. All right, so find the total entropy of your products, find the total entropy of your reactants, and then subtract the two. So products minus reactants again. But the units are going to be different for entropy. So you got to really be careful with this. The units are typically going to be joules per mole times Kelvin. You do need to pay attention to the balanced equation again, just like we did for delta H or bond energy here. So that's not new. That's going to be the same thing. But the difference here is, I told you kind of enthalpy and entropy are kind of opposites. A positive delta S is favored, right? A negative delta H is favored, but a positive delta S is favored. That means the entropy, the disorder, is increasing. So be very careful with this. You definitely need to understand that we want a positive delta S. The disorder is favored in nature. And if you're at equilibrium, your delta S would be equal to 0. You would not be changing your disorder here at equilibrium because your forward and your reverse are exactly the same. So just be aware of some of the differences here compared to enthalpy delta H. But again, we're going to be using this products minus reactants, but we do need to pay attention to the different units and watch our balanced equation here. Make sure you understand that a positive delta S is favored. More disorder is what nature prefers here. Let's do a pretty simple example here. We're going to calculate the entropy change at 25 degrees Celsius for this reaction using the given data. All right, so we've seen tables like this before. Notice the difference. All right, this is important to understand the difference. First, our units here for entropy are different, joules per mole times Kelvin. And notice the entropy for pure substances here, like solids and diatomics, is not zero this time. Remember, in order to have zero entropy, you'd have to be at 0 Kelvin, a solid at 0 Kelvin, which we've never reached. So you won't see any zero values here for entropy. So we know how to do this problem. It's just going to be products minus reactants, essentially. So I'm going to write my equation here. We know that our delta S would be equal to sum of all the S of the products minus the sum of all your S of your reactants here. All right, so all the products minus all the reactants, and we can plug in, but we do need to watch our balanced equation. So let's look at our products first, the SO3. So we're going to have 2 SO3s times the 256.5. All right, so that's all of my products minus all of my reactants here. So the first reactant I have is SO2, but there's 2 of them. So it's going to be 2 times the 248.1 plus, I have the O2 here, but there's just 1 of the O2s. So it's going to be 205.3. All right, but remember here, it's all of the reactants together. So all of the products minus all the reactants. Pay attention to your balanced equation. When you plug and chug this here, you do get negative 188.5. And remember, your units are different. It's joules per mole times Kelvin here. All right, and we need to look at what's going on here with this change in entropy as well. If you take a look, we got a negative value for our delta S. Remember, you can't have negative values for individual substances here, but you can get negative values for a process. So basically what this is saying is when this reaction takes place, our entropy actually decreases. That's not preferred, but there's other reasons why this can happen, and we'll talk about this by the end of this video. But we need to be able to look at this and understand why this took place. You would have to possibly answer questions about this. So why is this a negative change in entropy? Why did the disorder go down? Well, take a look at your actual reaction. If you notice here, all of the substances are gases. All right, so we're not changing state, so it's not going to be anything to do with that. But if you notice, on the reactant side, we have a total of 3 moles of gas, and on the product side, there's just 2 moles of gas. We actually decreased the number of moles of gas, so we are decreasing our entropy. There's going to actually be more organization here when the products form in this case. All right, so our entropy is actually a negative value, not preferred, but can still happen. So just by looking at the reaction, you can see why that value was negative. So you definitely need to be able to do that and do some analysis here like that for some of these entropy problems. But obviously you need to be able to do the math, products minus reactants, but all the products minus all the reactants. Pay attention to your units. Another example here, we want to find the entropy change for this reaction given the data here. So if we look at this one, all right, take a look at this reaction. I can see again, it's all gases here, but on the left side, I see 4 total moles of gas, and on the right side, in my product side, I only see 2 moles of gas. So again, I pretty much know that I'm going to be essentially decreasing the number of moles of gas here. I'm going to end up with a negative delta S. My disorder is actually going down here. Again, not preferred, but based on what I see in the reaction, I should pretty much know that my delta S value is going to be negative in this case, but now we can actually do the problem here. Remember, all the product minus all reactants. So our equation, delta S, is going to be equal to the sum of your S of all the products minus the sum of the S of all your reactants here. All right, so delta S is going to be equal to, our only product in this case is the NH3, but there's two of the NH3. Pay attention to your balanced equation. So it's going to be 2 times the 193 here. That's our only product that we have. All right, minus all of the reactants here. I notice that my first reactant is N2, and there's just one of them. So it's going to be 191.5 plus the H2, but there's 3 of the H2. So it's going to be 3 times the 130.6, and that's going to be both of the reactants here. So remember, it's all of the reactants together. So all the products minus all the reactants. Pay attention to your balanced equation. When you plug and chug here, as we said, you do get that negative value because of less moles of gas here in the reaction. So we got negative 197.3, but it's joules per mole times Kelvin for our entropy here. Just be careful. We know that a negative delta S is not preferred, but it can happen here. Based on our reaction, this does make sense. We need to talk about reactions that are thermodynamically favored here. All right, so any process or reaction that has both, all right, so you need both of these, a decrease in internal energy. So what that means is if you have a negative delta H and an increase in entropy, essentially a positive delta S, those reactions or processes are what we call thermodynamically favored. All right, essentially, we kind of already mentioned this. A negative delta H and a positive delta S are preferred in nature. So those reactions are considered to be thermodynamically favored. What that means is essentially they usually just happen. All right, they are favored in terms of the thermodynamics here, in terms of the energy and the entropy. And you have to use this terminology. All right, they used to use the terms spontaneous and non-spontaneous to describe these favored and unfavored reactions. So the idea is that if a reaction is favored, it would just happen spontaneously. You mix the things and then the reaction takes place spontaneously. So that's what the terms they used to use here for a favored reaction, but you're not allowed to use that on the exam anymore. You would have to say that a reaction is thermodynamically favored because it has a negative delta H and a positive delta S here. All right, you need to understand this idea. You need to use the terminology. Don't think you won't see the words spontaneous or non-spontaneous anymore, especially on older AP questions. You will definitely see them used. You just got to get used to using thermodynamically favored and thermodynamically unfavored. All right, we want a negative delta H, a negative enthalpy, and a positive delta S, a positive entropy here. If we have that for a reaction, that reaction will occur on its own, and we call that thermodynamically favored. This idea of being thermodynamically favored brings us to something called Gibbs free energy, or just free energy here. And we use the letter G to denote this. And this is just a measure of whether or not a reaction will happen without any outside energy. So, if you have a reaction about to take place, will it just occur on its own without needing any kind of push here? All right. So basically, by looking at this delta G, this free energy change, we can determine whether a reaction is thermodynamically favored or not. So it's kind of going to look at your delta H, it's going to look at your delta S and see if we have a thermodynamically favored reaction or not. If you get a negative value for your delta G, that means a reaction is thermodynamically favored. That means the reaction will just happen on its own without any outside energy needed. If you get a positive delta G, that means a reaction is thermodynamically unfavored. All right, so that's not going to be preferred here. It's going to need some type of outside energy to get it to go. it can happen, but you're going to need some outside energy to make that kind of occur. Delta G will be equal to 0 if you're at equilibrium. So as we go through this and talk a little bit more about delta G here, you're going to see it's very similar in terms of delta H. Like a negative delta H is preferred, well, a negative delta G is going to be preferred because that means a reaction will be thermodynamically favored. So we look at this Gibbs free energy, or just free energy here, this G, to determine whether or not a reaction can just happen without any outside energy, and basically whether or not a reaction will be thermodynamically favored. If you want to calculate the standard free energy change here for a reaction, we're going to be using an equation that's very familiar to us. It's going to be all of the delta G of your products minus all of the delta G of your reactant. Again, this is not really a new equation here. It's given on your equation sheet, just like your delta H, delta S equation. It's basically the exact same equation here, all of your products minus all of your reactants. The only difference here is we got to pay attention to units and stuff like that. It's going to be very similar in terms of delta H. Like I said before, it's going to have the same units as delta H. It's going to be kilojoules per mole. You do need to pay attention to the balanced equation, just like we did for our enthalpy and entropy. And delta G of formation here will be 0 for pure elements, again, and diatomics. So this, again, is very similar to delta H. Delta H had values of 0 for our pure elements and diatomics, and we'll see that again here for our delta G. But we did not see that for entropy. Entropy, the delta S, it's kind of the oddball here, different units, different sign is preferred. We don't see 0 for any of these pure elements, but delta H and delta G, we will. All right, so just remember here, all of the products minus all the reactants. Again, pay attention to your balanced equation and know that the units are back to kilojoules per mole for this. We can jump right in and do an example here. We want to calculate the free energy change for this reaction given this data. So we're going to do this. We already know that delta G would be equal to the sum of your delta G of your products minus the sum of your delta G of your reactants here. So all the products minus all of the reactants. Pay attention to your balanced equation. So we'll start with the products here. The H2O2, there are 2 of them, and according to the table, it's negative 120.4. That's my only product. So it's all my products here minus all of my reactants. So the first reactant I see there is the H2O. There are 2 of them. So it's going to be 2 times the negative 237.1. And then you do see that there is some oxygen here, but I don't see it in my table. That's because this delta G is just like delta H. These pure elements, these diatomics, are going to have a delta G of 0. So they're not going to be given. And you might think, oh my goodness, they didn't give it to me. But no, it's 0. So you don't have to worry about it. All right. So now we have all of our products minus all of our reactants. We paid attention to the balanced equation. When I plug and chug this, I get 233.4, and my units are back to kilojoules per mole. So obviously, if we look at this, this positive value now for our delta G tells us that this reaction would be thermodynamically unfavored. All right, a positive value for delta G tells you that your reaction is thermodynamically unfavored. And why that is, well, we could kind of look at that and think about it here. But the key is that you definitely need to understand that a positive value for delta G is thermodynamically unfavored. And there could be a bunch of reasons why this is taking place. Remember, there's going to be, delta H considerations, there's temperature considerations, and then there's entropy considerations here, as we'll kind of see. As we kind of keep going further here, we can actually see hopefully what's going on. We already know that nature prefers this low energy, this negative delta H, and this high disorder, or this positive delta S here. All right. But if you want to actually look at this, like what if you're doing a reaction and you have, a negative delta H, but then a negative delta S? Is it going to be preferred or not? Is it going to be thermodynamically favored or not? Because one works and the other doesn't in terms of delta H and delta S? Well, there's this equation here that we can use in order to determine delta G by comparing our enthalpy, our entropy, along with temperature. All right, so the equation is listed here. Delta G is going to be equal to delta H minus T delta S. And this is given on your equation sheet. You need to realize here that the temperature must be in Kelvin. All right, that's important. And because of our units, remember here, delta H is going to be in kilojoules per mole, but our delta S term is not. It's going to be in joules per mole times Kelvin. So you will need to convert this entropy here to kilojoules per mole times Kelvin. The Kelvin would cancel out with your temperature, and then you'd be in kilojoules per mole here to work with your delta H, because we want our units then of delta G to be kilojoules per mole as well. So we're going to use this equation. You might have to find your delta H first, then find your delta S, and then plug in this to this equation to see what we get for delta G, to see whether this reaction is thermodynamically favored or not. But definitely watch your units here as you're using this equation. There's actually another equation here now that we can use involving free energy, delta G, and it involves using the equilibrium constant, the K value. So it's delta G equals negative RT natural log of K. We call this the negative rattling equation, right? Because it looks like it spells out or sounds like rattling. This is given on the equation sheet. Some things to point out here, though. R is this gas constant, but be careful. It's a different version of R. It has different units. It's not the 0.0821 we were using for the gas law problems. It's the 8.3145 joules per mole times Kelvin version. It's on the equation sheet. You just have to know which one to use here. Temperature is going to be in Kelvin again, and K is your equilibrium constant. So now if you find delta G, we can actually use this equation to find our equilibrium constant. All right, so we can actually use the sign of delta G as well to predict whether or not K would be greater or less than 1 here, as you'll see. So we can kind of actually use this to get some information about K as well. If you solve for delta G and you want to think about what that means here for your K value, you just kind of need to think about what delta G means here. So if you calculate your delta G and you get a negative value, that indicates that the reaction is thermodynamically favored. So that means the forward reaction is going to occur, right? Well, a negative delta G, the forward reaction occurring, that means you have more of your product. So if you think about what K means, K, products over reactants, in a forward reaction being favored, you're going to have more products. So your K would be greater than 1. Products over reactants, more products means K greater than 1. Well, if your reaction is thermodynamically unfavored, you get a positive delta G here. Well, that means the reverse is actually favored. A positive delta G for a reaction as written would mean that the reverse reaction is favored. So the reactants are favored. Products over reactants, you would have more reactants on the bottom, so you would have a K value less than 1. All right, so you can actually use the value of delta G to help you figure out what's going to happen here with the equilibrium constant, but you got to definitely think it through. But we can also calculate that value for the equilibrium constant using that negative rattling equation. Let's do another example here. This problem wants us to calculate the delta H, the delta S, the delta G, and then the KEQ using the information that's given here. So I see the reaction, and then I see a table that has delta H values and S values here. Realize they could give you something like this and just say, find the KEQ. And you would need to realize that you have to find delta H, find delta S, find delta G so that you could use the negative rattling equation here. All right, this problem is kind of guiding you along, but realize you could just be asked for the KEQ, and you need to realize you do have to solve for all of these things before you can get to that point. All right, so let's just jump in and start. We'll do delta H first. We know that our delta H of the reaction is going to be equal to sum of your delta H products minus the sum of delta H reactants here. All right, products minus reactants. Pay attention though to your balanced equation. So when we look at this, the only product we have here is the SO3, but there's two of them. So it's going to be 2 times the negative 396. That's all of my products minus all of my reactants here. For the SO2, it's going to be 2 times the negative 297. And then notice the O2 has a delta H of formation of 0 because it is a pure solid or diatomic here. So that's going to be all of my reactants essentially, all of the products minus all of the reactants. When I plug and chug this here, I get negative 198. And then remember, this is delta H, so it's kilojoules per mole. All right, so that was pretty quick. Products minus reactants. Pay attention to the balanced equation. I just found the delta H here for this reaction. Now, when you look at your value of delta H, I can see that it's negative. So this reaction in terms of the enthalpy, the delta H here, is going to be preferred. All right, we get that negative delta H, which is preferred. So that's a good sign in terms of that. But we got to keep going here and see what's going on with the delta S, the delta G, and then eventually getting to KEQ here. Now we can move on to the delta S. We know the delta S here of our reaction is going to be equal to the sum of the S of our products minus the sum of the S here of our reactants. Pay attention to your balanced equation. So our delta S of this reaction is going to be equal to the sum of our products here. The SO3 is our only product, but there are 2 of them. So when we do this, we get 2 times the 257. Right, that's all of the products minus all of our reactants here. So we're going to have the SO2 that's going to be 2 times the 248 plus there's only one of the O2, and that has an S value here of 205. All right, all of the products minus all of the reactants here. All right, when I plug and chug this, I do get negative 187. And your units, though, for delta S are going to be joules per mole times Kelvin. All right, so be careful of that. Now, when I analyze the delta S that I got here, I can see this is negative. All right, so in terms of your entropy is actually decreasing here, which is not preferred. So now I have a preferred delta H being negative. I have a negative delta S, which is not preferred. This is where the temperature and that equation to find delta G is going to be important because all this information together will tell me whether or not the reaction is going to be thermodynamically favored or not. So now I have to move on to finding delta G. I'm not given the delta G information in the table, so I have to use my equation to find it based on the delta H and the delta S values. Now we are ready to find delta G here. Remember, our table of information did not give us anything about the delta G of formations here, so we couldn't use products minus reactants. We have to use our delta G equals delta H minus T delta S equation here in order to calculate our delta G. So we're going to need to figure this out based on our enthalpy, our entropy, and the temperature. But we do have to watch our units here. First thing I need to do is convert the temperature to Kelvin. So we know degrees Celsius plus 273 equals Kelvin. So we have 25 degrees Celsius plus 273 is going to be equal to 298 Kelvin here. But also, we need to convert our delta S that we found. Remember, our delta S is in joules per mole times Kelvin. We need to get that to kilojoules per mole times Kelvin here. So we found delta S to be negative 187, all right, joules per mole times Kelvin. So in order to get this to kilojoules, we're going to have 1,000 joules on the bottom for every 1 kilojoule. Joules will cancel, and now we will be in kilojoules per mole times Kelvin. So we're going to get negative 0.187 kilojoules per mole times Kelvin here. So that's my value of delta S in the correct units. So now I'm just going to plug into the equation here and solve for delta G. So delta G would be equal to delta H, which we had previously found to be negative 198 kilojoules per mole. Again, watch your units here, minus temperature times delta S. So we found our temperature to be 298 Kelvin times the delta S, which we converted to negative 0.187 kilojoules per mole times Kelvin here. So notice your Kelvin units will cancel, and then your delta H, delta S units would both be kilojoules per mole here essentially. So when we plug and chug this, we do get delta G being negative 142 kilojoules per mole here. Get used to kind of sig figging each step that you're solving for, your delta H, delta S, delta G, so on here. So we found our delta G to be negative. That tells us that this reaction is actually thermodynamically favored here. Our delta H was preferred, it was negative delta H, but our delta S was negative as well, which is not preferred. So when we take all this into account with temperature, we find that our delta G is actually negative. That indicates that this reaction is thermodynamically favored here. So you'll see you kind of have to consider delta H, delta S, and temperature when trying to see if a reaction is thermodynamically favored. If delta H was negative and delta S was positive, we would immediately know that the reaction is thermodynamically favored because both of them are preferred. But in this case, one was, one wasn't. So we calculated it just to prove that here we do get a negative value for our delta G. All right, so now we can work on finding the KEQ. Now that we have our delta G value, we can work on solving for K. Remember, we're going to have to use that negative rat link equation. So delta G is going to be equal to the negative RT ln of K. We already found the temperature here in Kelvin in the previous part of the problem, so we don't have to worry about that. But the other thing we're going to have to worry about here now is if you look on your equation sheet, the value of R that we are using for this problem, okay, R has to be in the joule per mole times Kelvin version of R. So R is going to be equal to 8.3145 joules per mole times Kelvin. So that means we're going to need to convert our delta G. All right, our delta G is in kilojoules per mole. We're going to have to convert delta G to joules per mole here. So pay attention to this. Realize this is the version of R that you need to use. It's on the equation sheet, but you have to know that that's the version you have to use for this equation, and you are going to have to convert your delta G here. So our delta G was equal to the negative 142 kilojoules per mole. So we just have to do 1,000 joules for every kilojoule, cancels our kilojoules. So our delta G here would be negative 142,000, and then it's joules per mole. All right, so just keep in mind, we had to convert our delta S term to use the previous equation, but now when you find delta G, we got to convert that to joules per mole. So now we can plug in here. We know our delta G is negative 142,000 joules per mole here. That's going to be equal to negative R, which we said R is 8.3145 joules per mole times Kelvin. And then we are going to times that by our temperature, which we already converted to Kelvin in the previous part, 298 Kelvin times the natural log of K here. So you just need to be careful with your math. So if we need to kind of go through this, the first thing you would do is multiply here. So you're going to multiply these two, the negative 8.3145 times your 298 Kelvin here. All right, so get the value for that. Then you will divide both sides by that value. All right, so you multiply those two terms together, divide both sides by that value. So when you do that here, you get 57.310730 0.03, and that would be equal then to the natural log of k here. So the very last thing you would do is you would need to do on your calculator the second ln button, and then essentially just times that by the answer you got here, the 57.3107303. So second ln, and then multiply that by your answer. You can use the answer button on the calculator, and then that will give you the value of k here. Essentially, you've got to take the inverse of the natural log in order to get rid of it so you can solve for k. I don't know if that's the right terminology, but I, in my head, say I got to get rid of the natural log, so I do inverse of the natural log, second ln button. And when you do that, you should get the value of k here being equal to 7.76 times 10 to the 24th. Don't be afraid here. If you get very large values for k, that can be perfectly normal. Very large values, very small values. Don't think you did it wrong, but this makes sense. A very large value of k here tells us that our products are favored, which makes sense because we already know that we have a negative delta G. This reaction is thermodynamically favored, so the forward reaction is going to take place. So definitely need to be able to take enthalpy data, entropy data to get delta G, and then go all the way to KEQ here. Even if you're not told to do the delta H, delta S, delta G, if you need to find KEQ and you're given that information, you have to find all those first and then plug into your negative Ratlink equation. Just watch your units here. And remember, K has no units, so we don't get any actual units here in our answer for K. We need to think about this favorability a little bit more here. All right, we said you do need to consider delta H, delta S, and the temperature when trying to figure out if a reaction is going to be thermodynamically favored or not. All right, so the easiest ones to think about here is, well, what happens if you have your preferred delta H and preferred delta S? So think about that. What that means is if you have a negative value of delta H, all right, we know that nature prefers this negative enthalpy change, a positive value for delta S, an increase in entropy, which is preferred. It doesn't matter what the temperature is because both of these are preferred. No matter the temperature, you're going to get a negative delta G here. You're going to get a thermodynamically favored reaction always because your delta H and delta S both had those preferred values, a negative delta H, positive delta S. So we don't even need to worry about the temperature. And then we could think about it on, the other end. If you have a positive delta H, we know that we don't want that. A negative delta S here, we know that that's not favored. Again, it doesn't matter what the temperature is. Both are not favored. You're always going to get a positive value here for delta G. It's always going to be thermo unfavored no matter the temperature. The real thinking comes in when you have one of them favored and the other one not favored. It's going to depend on the temperature here. So for example, if we say we have a positive delta H, we already know that that is not favored. But what if you have a positive delta S in your reaction? So your enthalpy is positive, which we don't like, but your entropy is positive, which we do like. All right. So it's going to come down to the temperature. If you have this scenario, one is favored, the delta S is favored, but the delta H is not. It comes down to the temperature. All right. At low temperatures, the reaction would have a positive delta G here, and it would be thermo unfavored. But at higher temperatures, you would have a negative delta G, and it would be thermo favored here. All right. And it all comes down to the math and that equation. If you actually look at your delta H minus T delta S, essentially with a high temperature here, you are essentially subtracting away a greater number here, which will give you a negative delta G. But there's an easy way to remember this. All right. It's a weird little saying, but this is something that kind of just works in my head. I just remember that when you're in these scenarios where one is good and one isn't, this only applies when you have, one good, one bad, if you will. At low temperatures, delta H wins. So I say in my head, low ho. It's just like I kind of say it, low ho. All right. That makes me remember that if you're at a low temperature, you look to your delta H because that's going to win. And if you're at a high temperature, you look at your delta S. I say high psi. All right. It reminds me that the higher temperatures go with the S. All right. So if we look at this situation, we already said here that if you have a positive delta H, that's not preferred, but a positive delta S is. All right, so one's good, one's bad. So we know low ho. At low temperatures, all right, so if you're at low temperatures, that means you look toward the delta H because the delta H is going to win. Well, delta H is positive, not preferred. You immediately know your delta G would be positive, not favored. But at high temperatures, high psi, all right? High temperatures here, we said that S wins. So when you look at the value for S, that was positive, that's preferred, you're going to get a negative delta G, all right? The same thing here in the opposite situation. If you have one good, all right, our delta H, what if that's negative? Well, that's good, that's preferred. But what if your delta S is negative as well? That's not preferred, all right? So we have one good, one bad, one preferred, one not. Look to your temperature. At low temps, low ho, H is going to win. So at low temperatures here, you look to your H, it's negative, that's preferred, negative delta G. All right, at high temperatures, high psi, you look to your S, S is negative, not preferred. All right, so you're going to be thermodynamically unfavored. Very easy to think about this in terms of when they're both good or both bad. It's when you get one kind of preferred, one not, that you need to look at the temperature and you need to remember low ho. Under low temperatures, you look to delta H. High psi, under high temperatures, you look to the delta S. This is definitely something you need to be able to do. You'll be expected to kind of look at these values for a reaction and predict what you would expect for delta G. So you really need to think this through and totally understand this and use the little trick to help you. One final thing to look at here are these misconceptions that always happen. You don't want to make these mistakes. So make sure you really understand these misconceptions and watch for them. Don't fall for any traps here. So first, people think that if you have a delta G that's greater than 0, so a positive delta G, that the reaction cannot happen, right? Because it's thermo unfavored, they think that the reaction cannot happen. Well, that's not true. Remember what delta G means. Delta G is talking about whether or not the reaction can happen without the input of external energy. Well, if you have a delta G being greater than 0, you can make that reaction happen by adding some external energy here to make it happen. Think about when you have a dead battery on your phone. You plug in the phone to the charger and it charges your phone. You had a process that could not occur on its own. You added some external energy and made it took place. So just having a positive delta G doesn't mean that the reaction cannot take place. You just need to add some external energy here. All right. Another big misconception is that if your delta G is very large and negative, so a very preferred reaction here, very thermodynamically favored reaction, people just think that, oh, it just will take place and it will be totally measurable and the reaction is just going to happen on its own. Well, that's not necessarily true either here. You can have a very thermodynamically favored reaction, but what if you have a very high activation energy? All right, that's going to be important here. If your activation energy is very high, you need to reach that minimum energy before this reaction can take place. So when it happens, you will have a very preferred reaction, very thermodynamically favored. But if that activation energy is too high, a very large negative delta G isn't going to matter here. All right, so just pay attention to this. You might look at a reaction and see, well, this reaction has a very, negative delta G, but it doesn't happen on its own. What's going on? It probably has a very high activation energy. So don't fall for any of these traps. Be very careful with these and make sure you understand these concepts.